I'm happy to present David Wajc, and he'll be talking on dynamic matching, rounding, and sparsification. David Wajc is an incoming assistant professor at the Technion in Israel. Until recently, he was a visiting computer scientist at Google. Earlier, he was a Motwani postdoctoral fellow at Stanford University, and earlier still, he got his PhD at Carnegie Mellon University's Theory Group. His research focuses on the design and analysis of algorithms, particularly ones dealing with uncertainty about the input, including online, dynamic, streaming, and distributed algorithms.
Thanks, Jason. Am I on? Where's my seat? Clearly. Yeah, so thanks for the introduction. Thanks to the organizers for inviting me. Before I dive in, I should say I have a bit of a soft spot for Simon, so it's very pleasing whenever I get invited here. It's also I'm moving to Israel next week, so this is something of a closure for me, which is not to mean this is like the end. Please invite me here again. So as I said, this place has a bit of a soft spot for Simon's. I've spent non-negligible parts of my PhD here. The first program I spent here, I think of as something of an academic birthplace for me. Most recently, I had an excuse to hang around Simon's when my wife was giving a talk at Women in Theory, and I spent the day thinking about a problem at Haas just across the street, and that kind of gave the last ingredient of a result I'm particularly pleased about that you heard about earlier today, and I'll tell you about a bit more about later on. So this is just to say that this institution, this particular building, it's great to be back. And with this personal motivation, I set out to make some slides with a little bit of help from from the family. And with that, let me maybe start actually telling you about something technical. So the topic of this talk will be the dynamic matching problem, which Soel already introduced earlier today, but even if you haven't seen it, we'll reintroduce it now. And in particular, I'll focus on key techniques that have played an outsized role, like a substantial role in the development of results for this problem. Okay, so the dynamic matching problem, the interface is kind of the same as pretty much everything we've heard in this workshop. So you have an n-node graph undergoing edge updates, so additions and deletions. And what you'd like to do is maintain some graph property. In particular, in this talk, we'd like to maintain a large matching, so a large node disjoint set of edges. High approximation ratio. As usual, the approximation ratio is just the multiplicative ratio between the matching we're maintaining in purple and the max matching, which I'll denote by mu of g. Okay, so this is a 2/3 approximation. So as you saw, those of you who saw the first talk of the day already know this problem has been studied a little bit in the last decade or so. Soel did a great work of kind of summarizing the type of time approximation trade-offs we have, and there was a good discussion about hardness for the exact problem. So I'll not belabor this too much. I'll just maybe try and kind of cluster three main regimes of time approximation that people have shown results for. So first, we know slightly worse than 1/2 approximation in polylog time. Other than this, we know some trade-offs like better than 1/2 in some poly n time, maybe sublinear in n. And most recently, we've developed a number of results for better than 1/2 in polylog time if you relax the problem and just allow for size estimation as opposed to actually maintaining the edge set. Question up till now? Good. So the goal of this talk is to focus on some key tools in the space, specifically key tools in the polylog update time regimes. And specifically, these tools are sparsification-based rounding and rounding-based sparsification. I'll make all of this clear soon, just to say there's been some work on this. Now, bearing in mind that the kind of overarching theme of the program is not just dynamic algorithms, but also applications of dynamic algorithms in speeding up static algorithms, I'll also kind of mention a few new adaptive dynamic data structures which you might find useful for speeding up algorithms. So these are fast dynamic almost maximal matching subroutines and optimal dynamic subset sampling algorithms. And I'll make both of these things clearer towards the end of the talk. All right, good. Without further ado, let me focus again. We want to focus on sparsification-based rounding. Question number 1 or question number 0 is what exactly do we want to round, just to kind of make sure we're all on the same page. And what we'd like to round is points in the degree-bounded fractional matching polytope. Okay, so it's a vector that assigns non-negative values to all of the edges, such that every vertex has sum of values incident on it, which is at most 1. If this is a binary vector, then that's exactly the matching constraint. No vertex can be matched more than once. And here we're just relaxing the integrality constraint. Good. What's a measure of quality of these such fractional matchings? It's just the approximation ratio. It's the number, the overall value assigned to the edges, so the L1 norm of x, divided by the max matching size. So I won't spend too much time talking about known dynamic fractional matching algorithms. I'll just briefly mention what these are, and that's kind of going to be the input to our rounding subroutines. In the fully dynamic setting, we know a number of algorithms that give slightly worse than 1/2 approximation in polylog or even constant time. So maybe correct me if I'm missing too many important ones, but if I am, that's what this ellipsis is for. We know better than 1/2 approximation in sublinear in n time, where the update time depends on how much better than 1/2 you get. And in the decremental setting, we know a number of 1 minus epsilon approximations and polylog time, originally just for bipartite graphs, but now also for general graphs. Okay, so we're gonna kind of take these as given, and we're gonna try and see if we can get some good integral matchings from these subroutines. Okay, so what's the interface for us? What we're going to have is a dynamically changing fractional matching x. And we get updates from the user that says, look, this edge E, I'd like to change its value to be, this edge E, I'd like to change its value to be V. And I promise you that the obtained vector x will remain a fractional matching. Okay, and naturally, what we'd like to do is maintain an integral matching that has value comparable to this fractional matching. In particular, we're going to ask for a 1 minus epsilon approximation. So those of you who have thought about the matching polytope I mentioned before know that this is only really doable for bipartite graphs, where the largest integral matching has value exactly the same as the largest fractional matching. So in general graphs, this is not quite doable. So just think about a triangle graph and assign values of 1/2 to all the edges. The max matching here is, of course, 1. And there's only 3 nodes here. Which is strictly less than it's like 2/3 this fractional matching. But I'll talk about what we can do for general graphs a little later in the talk. Okay, so towards the end. We're good with the setup? So without further ado, let me start with the first approach. Basically, okay, so the roadmap for the talk, I'm going to give you a little bit of an insight of maybe 4 papers in this space. Say a page or two, a slide or two apiece, just to kind of give you a sense of some ideas that were useful in this space for you to hopefully be able to use them in your own work. Okay. So the first idea in this space was this rounding via sparsification in joint work with Moab, Shiri, who I thought was somewhere around here, but I'm wrong, Sarel, and Cliff. Where you notice that we can basically use partial rounding of this fractional matching x to get a matching Sparsifier, so a sparse subgraph that preserves large matchings. Okay, I'll be a bit more precise about what I mean by sparse and how good of an approximation preservation of matchings I'd like. And then all we need to do is periodically solve in this Sparsifier, in this lazy recomputation approach. So basically, once if I maintain a Sparsifier in the background, then I can just compute a 1 minus epsilon approximation in this Sparsifier in linear time, or linear over epsilon, every epsilon mu steps. Okay, so what this is going to give me, well, the update time is obvious, though at least the amortized update time is obvious. It's just the work divided by the period length, so size of the Sparsifier over max matching times ep squared. And the approximation is essentially as good as the size of the max matching in the Sparsifier over the max matching in the host graph. Right? Just because over epsilon mu steps, nothing really changed. Very quiet. Someone ask a question. Okay. Good. So given this general framework, there's really two kind of quantities of interest we'd like to bound. For the update time, we'd like to upper bound the sparsity of the graph of the Sparsifier. Right, so that's this point over here. And for the approximation, we'd like to lower bound the quality of the, how well this Sparsifier actually preserves matches. Okay, so yes, Daniel.
I guess at every step in time, you basically know what mu of g is because you're solving a fractional problem.
Good. So the question was, how do I know mu of g? To actually be able to kind of estimate the length of these periods, presumably. Yeah, so given this fractional matching, I already have some constant approximation. So it doesn't have to be epsilon mu, but something in that ballpark. Other questions?
The Sparsifier itself you can compute very fast.
Good. And good. So Sebastian's question is, how do you compute this Sparsifier? And that's pretty much going to be the focus of most of what's coming, right? So how much time do you need to spend for the Sparsifier?
And you're just using Sparsifier loosely without defining what properties you want to preserve?
So I guess I mentioned this in passing. Sparsifier, I'd like this sucker to be sparse, and I'd like it to preserve matchings. That's about it. Other questions? Okay, well, we're on a roll with questions here, so this will become more and more interactive. This is great. Okay, so our first approach at computing such a Sparsifier, following up on Sebastian's question, is, in hindsight, probably the most natural thing you could think of. Whenever I change the value on a particular edge, I'll just sample or resample that edge based on this value. Okay, so this new value, I guess the new value is v. So I'll now decide whether or not I add or keep this edge e in the Sparsifier with probability v times log over ep squared. And I'm externalizing the dependencies on epsilon. It'll be a bit clearer why later. But for now, this is just to kind of point out that this dependence on n and epsilon is, for those of you who kind of want to think of where this is going, this is exactly where you think this is going. There's going to be some Chernoff bounds coming. Okay. So for our analysis, maybe 3 applications of Chernoff will tell us that this is a good Sparsifier. So first of all, with high probability, the size of the Sparsifier is going to be the x norm, the L1 norm of x times log over ep squared. The L1 norm of x is not much larger than mu, maybe like 3/2 times larger. So this is basically mu times log over ep squared. So what we get is log n over ep to the 4th. Okay. As for the approximation, what we're going to do is we're going to take a more or less unbiased estimator of x. So for every edge e, if it's in the Sparsifier, we'll give it a fractional value of epsilon squared over log n. Okay, so this is supposed to wash out with this probability over here. So the expected y value of every edge is basically its x value, maybe times 1 minus epsilon for a bit of slack. Okay, what does this buy us? Well, 2 things. First of all, the L1 norm of y is essentially the same as the L1 norm of x. Again, just a simple Chernoff bound. And in addition, the vector y is a fractional matching in S. Y, the expected norm for every vertex is less than 1. It's like 1 minus epsilon. And so just by Chernoffs, and since all of these values are small, you're still, with high probability, you're not going to violate the degree constraint for any vertex. Okay. So what we get from this is that the max matching in this Sparsifier is at least the value of this fractional matching in y. So remember, in this talk, we're only talking about bipartite graphs. So the max integral matching in S has value at least the max fractional matching in S, which we just said is basically the same as our initial fractional matching, which we wanted to round. Good. So just to kind of summarize, what we get here is log n times epsilon minus 4 time to periodically compute the matching. For Sebastian's question about how much time we spend on maintaining the Sparsifier, nothing. Right? We spend constant time. Whenever I change the value on the edge, I just resample. And the approximation ratio is 1 minus epsilon times whatever the approximation ratio of the fractional matching was. So
So this kind of Sparsifier makes a lot of sense in this setting. What I was wondering is, do you know that other constructions of Sparsifiers don't work preserving matches?
other notions. Okay, so just to repeat the question and maybe make sure I understood. Are other notions of Sparsifiers useful? So then other Sparsifiers than this particular Sparsifier? Or?
Yeah, just because, I mean, people have studied Sparsifiers for different things, and it'd be nice to have, you know, one kind of construction that works for many settings. So is it plausible that there is a Sparsifier that's not customized to matching, but also works for matching?
That's a great question. Off the top of my head, no clue. Good question. If anybody else wants to chime in with a solution. Jason.
I like to comment like this. The random sampling is also done in like cut sparsification, for example.
Sure.
Is it similar? Like, are the analyses similar, or?
I mean, I just told you the analysis. There's not a lot going on here. It's just a couple of turn-offs on top of each other. That's Sebastian.
Are you going to say something about that?
Sorry?
Adaptivity, right? I mean,
Fantastic. Ask this question again. Ask this question again in 2 slides. Okay. Thanks. I'm not going to repeat the question because it's spoiling the next slide. Other questions? Okay, awesome. So I'm going to try and keep things at this like abstract level of I only care about rounding the fractional matching without talking about the integral problem, the kind of integral results we get from this. But just to give you a flavor of the types of corollaries you'd get from this. So for example, rounding the SOTA 17 worst case update time algorithm of Cheyenne, Monica, and Danupon, you get a half minus epsilon approximate dynamic matching algorithm with polylog worst case update time. So the same result was obtained concurrently by Moses and Shai, both of whom are in the room with Cheyenne. But just to kind of say, here's a kind of simple way. Given a fractional algorithm, you get a fairly simple algorithm. Okay, now addressing Sebastian's question about adaptivity, the one downside of this algorithm, as well as that of Moses and Shai that I just mentioned, is that this algorithm only works for an oblivious adversary. Oh, so some of the animations are broken here, but so imagine you can't see this. Okay, so what's the problem? The adaptive adversary can repeatedly delete the sampled edges. Right? This is a very sparse graph. So if you think just say about a star, then the sample will really only give you a small number of edges here, and well, the adversary can just decide, well, in that case, I'm going to delete those edges. So at least this approach seems pretty broken. Okay, and I guess I don't have to belabor this point too much within for this audience, but maybe for people watching this talk on YouTube later on, I should kind of reemphasize that we care about this notion of adaptivity in order to be able to use our dynamic algorithms to speed up static algorithms or within other algorithmic subroutines. Right? This is the whole concept of this program. Okay, so take 2 at the problem of rounding. Okay, we saw a very simple algorithm that will give you lossless rounding in bipartite graphs against an oblivious adversary. Let's try and do randomized, but in an adaptive setting.
David?
Yes.
Just slightly confused. Is the issue that the fractional algorithm isn't adaptive, or is it really just
the fractional algorithm is deterministic, so that's as adaptively robust as it gets. Yeah. The problem is just I'm only focusing on a subset of the edges, and if the adversary knows that, then you could just say, look, you tell me what the answer is. Oh, it's this edge? Okay, delete that. What's your answer now? Just keep deleting until you run out of edges.
I'm getting confused about why the fraction, why was it correct in the previous slide?
This is the same algorithm from earlier.
Yeah.
So
Where did the
So think of like the simplest fractional matching for this solution. So let's say just 1 over n across all the edges. You're sampling log n many edges. I, as an adaptive adversary, are just going to destroy this. I'm just going to destroy this in log n steps. The fractional matching doesn't need to change. It's still pretty good matching, fractional matching. But at least for this algorithmic approach, I'm hosed. If you follow the example, that's great. If not, it's not too crucial. Just take it at face value that this does not work against adaptive adversaries. OK. So idea number 1 to make things work against adaptive adversaries is instead of actually maintaining a Sparsifier, just periodically computing one. Okay, I don't really care about a Sparsifier during these periods when I'm between my matching computations. So let's just do that. Okay, so we're going to do periodic Sparsification and compress steps 1 and 2 of the high-level approach we saw earlier. So what we're going to do is periodically partially round x to get a Sparsifier s, and then solve an s. That's the only high-level difference. So we round and compute this matching every epsilon mu steps. We're going to take the time that it takes to round plus the matching computation, and the update time will change appropriately. Okay, so now we also have to factor in this rounding step. Okay, so the analysis is more or less the same as before. We need to bound the time to round plus the size of the Sparsifier over the matching size. The approximation, again, is the quality of the matching Sparsifier. And as far as adaptivity, all we really need is that our data structures that allow us to periodically run steps 1 and 2 together work against an adaptive adversary. Okay, so for example, the fractional matching is deterministic. That's great. We can use that. And then whatever other data structures we need to be able to quickly partially round our fractional matching and solve, okay, so computing the matching, in this time, we know how to do deterministically by Duan and Petty. So I have to tell you about rounding and what data structures I run in the background. Yes, no? Daniel, ask a question.
So what is the difference that you
Good. So the difference is that previously, good. So let me go a couple of slides back. So before I was maintaining the Sparsifier all the time in the background, and then computing a matching. Here I'm saying, screw that, maintain whatever data structures you need, but only compute the Sparsifier just before you compute a matching in it. Excellent. All right. OK, so how do we compute a Sparsifier? OK, so in comes the second idea, which is sampling via edge coloring. So what we're going to do is we're going to look at subgraphs that are induced by edges with essentially the same x value. The same, say, like power of 1 plus epsilon. And then in order to sample edges in bulk in a correlated manner, we're going to start by edge coloring these graphs. Okay, so a quick reminder, an edge coloring of a graph is an assignment of colors to each of the edges so that no vertex has 2 edges of the same color. Okay, so in other words, it's a decomposition of the graph into matchings. Every color is a matching. You clearly need at least delta colors, right? Every max degree node needs at least one color per edge. And that's more or less the right answer. Delta or delta plus 1 is the number of colors you need. By the degree constraint, since all the values in the subgraph are basically assigned to these edges are 1 plus epsilon to the minus I, no node has more than 1 plus epsilon to the I many edges. Okay, so I can color this graph with roughly 1 plus epsilon to the I colors. I'm going to allow myself a little bit of slack, maybe color it with C times as many colors. C can be like 3 or something, and that will allow me to maintain this adaptively. I won't tell you how. It's a very easy exercise, but believe me. Okay, so I've colored this graph into a small number of matchings. And now what I'm going to do is sample a small number of these colors, small number of these matchings. Okay, and what we get from this is, this over that, things wash out, the C's wash out. 1 over this is the XE value. So what we get is that this new Sparsifier contains each edge with exactly the probability we were using for the independent sampling earlier on. Okay, so again, number of colors divided by, number of colors sampled without repetition divided by number of colors is log n over epsilon squared times roughly 1 plus epsilon to the minus I. If you're following the calculations, great. If not, that's not really the key point. The important thing to take away from this is that this allows us two things. First of all, with slightly more sophisticated Chernoff bounds, but not a lot more sophisticated, we can argue that we get the same approximation as with independent sampling. The key difference in the analysis is that now edges are not sampled independently, but you can show that they're negatively associated, and you still get the same types of correlation. If you're interested in learning this one nice probabilistic tool sometime in the near future, I recommend this primer. I think it's a nice I'm working on expanding this also, so if you want to hear about some more cool stuff, ask me about it afterwards. OK, so the approximation is just as good as independent sampling. Now, what about the update time of this rounding scheme? The size of the Sparsifier is actually fairly easy to analyze if you don't care about the exact logarithmic dependence. This Sparsifier is made up of, say, at most log squared n many colors, log squared n many matchings. Right? There's log n many ranges of I. And each one of these, I'm sampling log n colors. So log squared n many colors. A color is a matching. So and by definition, it's most the size of the max matching. So the size of the Sparsifier is at most mu times log squared n. Okay. So what I get here is that the update time is size of the Sparsifier, which I just told you is mu times log squared. So it's basically log squared n. If you're a bit more careful, you could shave one of these logs off. We're happy with this example? Sushant, yes?
So you're doing this for all 1 over epsilon?
I'm doing this for all log n over epsilon many ranges. Yeah, for sure.
I see. So now, in some sense, instead of independent sampling, you're trying to sample matchings.
I am sampling matchings instead of independent sampling, exactly. So correlated sampling as opposed to the independent sampling.
And the only reason you're doing this is because you can do the first part adaptively?
The only reason well, I guess there's two reasons I'm doing this. Good. So I can do this part of that. Sorry, I'll repeat the question. Is the only reason I'm doing this because I can do this adaptively? The first step adaptively. I think one key aspect here is the fact that I'm, in some sense, maybe I should have written down the time for rounding, which I think is maybe the more important aspect here. So the time for rounding here is, well, I'm sampling log n colors, log n ranges. This is like polylog. You can worry about what log exactly, but some polylog. And then I'm just writing down the Sparsifier. Okay, so rounding is very cheap. For the independent sampling, if I were to independently round every epsilon mu steps, I'd have to go edge by edge, at least naively. I'd have to go edge by edge and flip a coin for that edge, which would take me m time instead of something proportional to max matching, which is at most n. Jason.
Could I add on to that?
Sure.
So like my interpretation is like by coloring the edges, you're kind of like hedging your bets over all the possible edges your adversary can delete.
Mm-hmm.
So instead of like having just one set of like a Sparsifier where the adversary can just delete all the edges, you have like a bunch of Sparsifiers. So the adversary cannot like kind of kill you by just like focusing on one single Sparsifier. You're kind of like hedging your bets over all the edges. Is that?
That's an interesting interpretation. I don't know that's quite what's going on, because at the end of the day, at least the way the analysis comes out, I'm pretty much saying this is the same as sampling independently. The key difference is that I'm able to resample fresh every epsilon mu steps in time proportional to mu. Okay. So I had a question here, yes.
The reason is only saving you a polylog, right? Because you only have polylog and matchings.
Right. I'm saving, no, Sushant, so I'm not saving just the polylog, right? I'm saving the time to round is mu as opposed to m.
Well,
as opposed to number of edges.
Jason was proposing is only polylog and different. Like every polylog and round you could hit the same set of matchings. So his argument doesn't win any more than polylog. I was saying it doesn't suffice. That's all.
I see. Yeah. If you're saying like there's log n, so if you think about the star example, if you just say, look, I'm going to take a larger polylog, the adversary can still shave off like some small polylog number of edges and still leave you with an empty Sparsifier, unless you're able to recompute fairly quickly.
I guess
if that's not so clear, we can chat about
yeah,
this more.
Okay.
Yeah. So the other question.
So I'm still a bit confused about why independent sampling doesn't work. So all of the edges have the same XP value up to 1 plus epsilon factor, right?
Sure.
So you have a set of M edges, and you want to sample each one independently with probability XP. So of course, yeah.
Oh, this can be simplified a lot. I know where you're going with this. Yes, this can be simplified now. Yeah, for sure.
So you don't have to go through the edges one by one. You
Right.
can just generate it.
Just sample a binomial. Yeah, for sure.
Yeah. Just sample a what? Can you, what is
A binomial. So if I mean, this is with the benefit of hindsight, this is a simpler way of doing this for sure.
So every edge has a value, an arbitrary value. You can
So I've got like a certain number of these edges. Okay. I want to sample each one of these with essentially the same probability. I can just draw a binomial to figure out how many of these I have.
Oh.
Right. Then run like a Knuth shuffle or something and just decide which one of these edges I took.
Okay.
It'll take time proportional to the output. Yeah, thanks. Good. Other questions? Same. Okay, so far we've seen an oblivious algorithm, we've seen an adaptive algorithm. What's the next step? Sorry? Deterministic. All right, thanks. Right, so the downside of the algorithms we've seen so far is where the hell do you find random bits? All right, there's been programs here and elsewhere thinking about these types of questions. So let me briefly mention one deterministic approach and then move on to yet another. So this one is based on ideas of a paper of Cheyenne and Peter and subsequent de-amortization by Peter, which again looks at the same induced subgraphs of edges with the same values. And what we're going to do in each of these is essentially run pipage rounding. So what do I mean by this? Okay, so Daniel's nodding vigorously. That's great. So we just walk around the graph. We get a bunch of paths and cycles. And in each one of these, we take, say, either the red or the blue edges, whichever are more plentiful. We double the value on whatever we actually kept, rinse and repeat. Okay, this will roughly preserve the total value as well as the value for each node, at least within the context of these GIs. And for technical reasons, you stop at some epsilon value instead of going all the way to integrality, basically because if I do this for every one of these possible values, I could round a bunch of edges to 1 and get some issues. That was a bit fast. Okay, so if I get a bunch of these graphs, I'm kind of in parallel trying to partially round these. And I'm claiming that I preserve the degree of the nodes. But because of a rounding up issue, right? So if you think, for example, about this node, let's say the value here was a half. I round this up, now it has a value of 1. If I also round this in another one of these subgraphs, then now all of a sudden I'm going to have a bunch of edges incident on this. Okay. If you follow that, that's great. If not, this is more or less the right level of abstraction.
Are you assuming it's
bipartite? I'm going to assume it's bipartite. I'm pretty much the entirety of the talk. I'm going to assume the graph is bipartite, and then I'll have maybe one slide talking about not bipartite. Other questions? Yes.
So basically, do you want to do this every time you want a sparse graph, right?
Fantastic. Okay, so right now I just gave you more of a static approach for this. And now let me tell you how I'm going to make this dynamic. Basically, what we're going to do. So this subroutine it's not too hard to see. Basically, runs in linear time. Right. So every step I'm having the number of edges. So basically, it just costs me the number of edges for each of these subgraphs. And what I'm going to do is I'm going to apply this sparsification for the subgraph GI whenever the number of edges in it changes by 1 plus minus epsilon factor. Okay, so it's going to cost me, the number of edges in G over epsilon times the number of edges in G. So this step, the sparsification time costs me 1 over epsilon. Okay, this is the amortized cost of this. And since I only actually I don't need to do anything until the value changes by more than 1 plus minus epsilon. I'm basically a 1 minus epsilon approximation. Okay. So without going into too many details, the size of the Sparsifier is basically the max matching times polylogs. And what we get from this is a 1 minus epsilon approximation in size of Sparsifier over max matching, so still polylog update. If you follow this, that's great. If not, maybe just this pipette rounding thing, subroutine is good to remember because we're going to reuse it shortly. Let me just summarize what was the state of the art until maybe a year ago. So the first algorithm we saw was this oblivious rounding approach, which had epsilon to the fourth dependence on epsilon, logarithmic dependence on n. I then showed how to get the same results adaptively with high probability, and in expectation with constant probability, you can even drop the dependence on n. The deterministic approaches that followed later give you some poly-epsilon, poly-log dependencies, which are quite a bit higher, but probably could be improved. But I'll point out that there's kind of a fundamental barrier at improving these approaches that we were stuck at until fairly recently, which is this epsilon to the fourth seems pretty hard to overcome for two reasons. Okay, so there's two factors. The first is the periodic recomputation, which says take size of Sparsifier over epsilon, size of Sparsifier over epsilon, that's the time to compute a large matching. Every epsilon new steps, your Sparsifier has to at least contain a matching. So best case scenario, your Sparsifier has size mu, that's already an epsilon to the -2 factor. And actually all the Sparsifiers we knew how to compute had the quadratic dependence on epsilon. Okay, so you really have to take the product. This is a good time to plug in a recent paper with Cheyenne, Peter, and Aaron, which allowed us to sidestep, basically break this barrier quite significantly, and in particular, effectively meet what seems like a barrier, almost unconditional barrier, barring some philosophical discussions we had yesterday. The best recourse bound you could hope for is 1 over epsilon. So for every change to the fractional matching, you would need to change 1 over epsilon edges. So this 1 over epsilon seems to be essentially the best you could hope for. And let me also point out, I have like 3 rows here, so let me tell you exactly what we get here. So deterministically, we get what we knew how to get adaptively with high probability. For the adaptive high probability regime, we get sub-polynomial dependence on n, in particular poly-log-log dependence. And we can even get a constant probability output adaptive algorithm with constant update time. Where I'll point out, output adaptive here means that the adversary knows the changes to the output, but does not know your internal state, which I'll point out is good enough for all the applications where we care about adaptivity. Right? So, all the algorithms up until this line were kind of cryptographically secure. So even if the adversary knows what's going on under the hood, you're still doing well. Good. So let's see. So we're questions.
With the epsilon to the -4, does one of the epsilons come from the Duan-Petit matching computation?
Yeah. So the periodic recomputation is Duan-Petit over epsilon mu. So that's like 2 of the epsilons come from that, basically.
If you have a linear time matching algorithm, would you shape?
If you have a linear time, okay, fantastic. So one of the epsilons you could replace with, say, a sub-polynomial term using Sushant and company's near linear time max matching algorithm, for sure. Then this next column becomes kind of incomparable. Okay. So how are we for time? Okay, so I'll probably. Okay, let me skip maybe one of these slides. I'll just kind of say that there's a nice idea here about rounding bit by bit from least significant to most significant bit. Sorry, Jason, how much time do we have? Yeah. Okay, so let's maybe skip this slide. For those of you watching the recording afterwards, you can slow down here and kind of read things a bit better. I'll just point out that the kind of black box result we get here is a 1 - epsilon approximate dynamic bipartite fractional matching rounding algorithm with L squared over epsilon update time, where L is basically the bit precision of the x values. Okay, so it's log of min non-zero value 1 over xe. So if you remember from the table earlier, I promised you better dependence on n. L could be as high as log n. So to get better results here, we have some nice kind of pre-processing idea of partial rounding to decrease the range of values. So just to give you a flavor of this, to get an oblivious result, you could use the simple rounding approach I mentioned earlier. will get you all your values to be epsilon squared over log n. And so L will now become log of this thing, which is basically log log n. Okay, so you get a log log n squared update time. The more interesting approaches we get for partial rounding in our work rely on some other new ingredients, kind of effective ways of getting multiple Sparsifiers wholesale. So you spend more or less the same amount of time you spend to compute one Sparsifier, at least in an amortized sense. You could get a bunch of Sparsifiers and then allow yourself to kind of switch from one to the other. And another interesting subroutine, which I'll briefly mention, is we give a new output adaptive dynamic subset sampling data structure, which simple as it is, I think might actually find some applications elsewhere. Okay, so let me maybe spend a couple minutes on some tools that were developed by this line of work and for this line of work, which I think you might be interested in. So up until now, the entirety of the talk focused on bipartite graphs, but I promised Chandra I'll tell him about general graphs, so let me spend one slide on this. Generally, we cannot round fractional matchings in general graphs. And nonetheless, the known dynamic worse than half approximate fractional matching algorithms are known to be roundable. So in particular, in this first rounding paper, we showed that you can use them to get an integral matching algorithm with the exact same approximation ratio, even in general graphs. Exact same up to 1 minus epsilon. And moreover, in SODA this year, what we showed is that you can use these to get adaptive polylog time, almost maximal matching algorithms. In the most recent paper, we sped this up and also showed how to get this deterministically, which should almost completely de-randomize this paper, if not for the use of sublinear time algorithms. So the notion, I'll skip the exact definition. It's more or less what you think. It's maximal so long as you squint at the graph and ignore a small number of nodes. And these almost maximal matchings seem to be useful pretty much in the same way that maximal matchings are, if you're OK with a small error. So I think whatever algorithms you have where you're interested in dynamic maximal matching algorithms, consider using dynamic almost maximal matching algorithms. They might give you exactly the same results. Okay, I'll also mention that we have this adaptive dynamic subset sampling algorithm. The interface is more or less what you think. You update the probabilities for every element, and you want to support queries which output a set from a product distribution. So every element is picked independently with probability pi. Studied quite a bit before, and we give the first, to our knowledge, output adaptive algorithm for this problem. All right, let me wrap up real quick. Sorry, I'm a couple minutes over. So just to summarize, this dynamic matching rounding problem has been studied quite a bit before and underlies pretty much all of the polylog time algorithms that we know in this space. For bipartite graphs, this means that it's enough for you to focus on the fractional problem. If you want to get a strong result for a dynamic bipartite matching problem, it's OK for you to focus on dynamic bipartite fractional matching. For general graphs, the history hints that all the relevant dynamic fractional matching algorithms are roundable. So possibly the same could be. The most appealing question for dynamic matching broadly is getting the same type of results that we got for size estimation for the actual problem. So actually maintain a better than 1/2 approximate matching in polylog update time. As far as techniques and tools, I guess I spent the talk telling you about rounding via sparsification via rounding. This seems very powerful for matchings. Can you use it for other problems? The adaptive subroutines I mentioned, I think, have further applications, so I beseech you to find the applications. And actually, even dynamic matching, at this point, we have a number of pretty strong adaptive dynamic matching algorithm, just approximate matching. We don't even have any compelling applications for this yet. So this is one of these cases where the tools predate the applications. I urge everyone here in the room to think of such applications. And with that, let me thank you for your time.
Thanks, Dave, for the great and interactive talk.
Thank you.
We're running a bit over time. Maybe 1 or 2 questions, if anyone has any. Sebastian?
So could you use this proactive recycling technique? Of course, now you have something deterministic with stronger weights.
So the question is, could we use this proactive resampling technique? I guess what would be the hope here? I mean, as you say, we already have deterministic algorithms that seem to be. That's a good question. Maybe Aaron has a better idea. I don't know. Unclear.
Maybe we can take that offline.
Yeah, for sure.
So, what is the result on rounding? What do you mean by that? I just. General graphs, what is the statement? What do you mean? So, in the static setting, what is it that you are saying? And
good. So the result for general graphs is that the particular fractional matching algorithms that we know how to maintain in dynamic settings. This, I guess, actually is not the only one we know, but let's focus on this one. This has particular structure that allows you to show that actually it contains an integral matching of essentially the same value. So this is a half minus epsilon approximate fractional matching. You can show that it's no better, but its support also contains a half minus epsilon approximate integral matching. So in that sense, it's roundable.
You don't lose.
You don't have to lose the integrality gap, basically. Yeah.
Could you show the slides on subset sampler? I just want to understand what does it do.
You're all welcome to read. Is that it?
Oh, well, maybe I was going to ask you to change slides, but
Fatima reads quickly, so it's fine. Just yeah.
But I wasn't quite clear where the improvements came from that got you to like 1 over epsilon. I mean, so like the.
Yeah, I mean, I guess
Or do you?
Good. So I'll try not read through the slide, but I'll just mention one point here. Basically, we skip exactly the use of Duan-Petit in periodic recomputation. We just show how to maintain, we round direct to integrality, as opposed to all the previous approaches that were blocked at, getting a Sparsifier of size mu over epsilon, actually nothing was as good as mu over epsilon, so mu over ep squared, and periodically computing a matching. Here we just round all the way to integrality, and we're good to go. And for general graphs, we managed to improve the size of Sparsifiers from, say, mu over ep squared to mu over ep. So we also get improvements for general graphs. I feel like the result for bipartite is probably more compelling, where we really just, none of this like periodic recomputation, just give me a matching, and I want you to always have a matching at hand. Aaron.
For the dynamic set sampler,
Yeah.
I only just looked at the slide, so maybe I'm missing something.
Yeah.
Can't you do the trick that I think Sohail was saying? Like, why can't you just like count the number of things at different probabilities, and then like figure out how many?
Good. Yeah, that also works, and that we did not write for this version, but that's what we have written up is a little more involved even than what we just said. Aaron, Sidford, if you remember, we also talked about this at some point. By just sampling from a binomial for each range is effectively as good if you don't want the exact probability. Whereas what we had here, if you actually care about exact probability, I guess that's maybe the difference, right?
That has to do with that caveat.
Right. I see. Good. One other aspect, if you want to do this per range, like if you're rounding probabilities, even if you don't care about if you don't want to sample with probability exactly pi, you're okay with pi over 1 plus minus eps. You have to bear in mind that this 1 is no longer a 1. Now it's like the number of ranges of probabilities that you care about. This would be like a log over eps.
Oh, okay.
So I think that's probably what's nicest about this approach, as opposed to just sampling from binomials and shuffling on top of that.
And these are worst case guarantees in your?
These are expectation and expectation, of course.
All right, in the interest of time, let's take any questions offline. Thanks again, the speaker.
Thanks.